to see you there. Well, now that you're here, you want to hear about some cycloids over in the talking area? The cycloid was first discovered by Charles de Beauvais in 1501. He used it in his proof of squaring the circle, but that was about it. It wasn't until 1640 when Galileo wrote a letter explaining that he'd been thinking about the cycloid for 50 years. One of the things he did was trying to find the volume under the curve of a cycloid. He did this by taking a piece of metal and cutting it into shapes similar to a cycloid and weighing them, trying to figure out what the volume was. He then tried to figure out if there was a ratio between the volume and the radius of the cycloid. He found it was roughly 1 to 3. He thought this was ridiculous and just threw out the answer. History later proved that he was right, but we'll get to that later. In 1657, Richard Huygens found that the period of a simple pendulum was in fact proportional to the amplitude, meaning that if you pulled the pendulum out to here, it would be a different period than if you just pulled it out to here. Trying to fix that to make a more accurate clock, he constrained the path of the pendulum to a cycloidal path, meaning that the path of the pendulum didn't follow that of a circle, but that of a cycloid. This made the period independent from the amplitude. In 1658, Blaise Pascal wanted to find a way to make things more interesting. So he devised a competition. He took the figure you see here and said, okay guys, let's find the center of gravity of the figure BCD, or of the region BCD, and also find the volume and center of gravity if BCD is revolved around the line CD, and the same if it's revolved around a BC. Only 2 people actually submitted results. One of them was John Willis and the other Robert Duvall. Neither of the answers was considered right, unfortunately, so no one won and it kind of faded off into history until now.
The cycloid has 2 different applications. The first is the Christochrome curve, in which John Bernoulli wanted to find a curve in which a ball rolled from point A to point B would get to point B as fast as possible. The solution to this problem is the Christochrome curve. It's an inverted cycloid. This inverted cycloid not only is the fastest point from point A to point B, but any point in between A and B will take the same amount of time for a ball to roll from any point along this line to get to point B. So any point between A and B rolled down this curve will take the same amount of time. The tautochrone or isochrone curve is the pendulum curve that Peter talked about earlier. Tauto is Greek for same, and iso is Greek for same as well. And chrono is Greek for time. And so same times, so it takes the same amount of time no matter how you do it. The Christochrome curve, the one that I was talking about earlier from point A to point B, the fastest time, Christos is Greek for the shortest, and chronos is Greek for time. So it makes sense that it would be called the shortest time from point A to point B, that curve.
The cycloid is a parametric equation, which means that there are 2 separate equations, an equation for the x-coordinate and an equation for the y-coordinate, and then the graph of the cycloid is really a graph of the x and y coordinates combined. So the 2 equations given above are the equations for the x and y coordinate, and Troy is going to solve for the general equation of a cycloid and set it equal to x. Because the y equation only has one t, Troy is solving for that t and then plugging that in any place that he sees t into the x equation. Here Troy is showing you how he went from y over r equals 1 minus cosine of t to t is equal to inverse cosine of 1 minus y over r. Troy is now plugging in what he solved for just earlier, and he is plugging it into the x equation, and he is finding that there is going to be the sine of a cosine, or inverse sine of a cosine, and so we're going to have to build a triangle to come up with that answer. Inverse sine is asking for us to find the side length of a triangle value, and since we know the cosine value, which is 1 minus y over r, we can construct a right triangle and use Pythagorean values and rules to solve for sine. After we find the side length, we then want to put that into sine and find out what sine is equal to. So Troy is plugging it into where the sine value was, and we're going to simplify that down. Remember that when we plugged in the t's in for the t values in the x equation, there was an r out in front, so the r is really multiplied through the entire equation, which is why there is an r out in front of sine. And then to keep the things on the both sides of equal sign equal, you have to multiply the other side by r. You can then factor out a y over r, and then when you bring in the r from the outside of the radical to the inside of the radical, since the r equals the square root of r squared, you really can put an r squared on the inside of the radical, and then when you multiply it out, the r's will cancel. After figuring out what sine is equal to, you can take the sine, plug it back into the original equation with what Troy had solved for earlier, and then you are left with your final equation. So you start with the two general equations that Troy was using earlier, and because we're finding arc length, we're going to set up an integral from 0 to 2 pi, because that is one period of a cycloid, and then we are going to use a variation kind of the distance formula, change in y and change in x, because if you think about it, kind of like change in y and change in x is like a triangle. You're building small pieces, and that is what the integral is the integral breaks stuff down into smaller pieces and then adds them up. So we take the x equation, find the derivative of that, then we take the y equation, find the derivative of that, and then plug them into change in y squared plus change in x squared. Here I am multiplying out the r minus r cosine quantity squared. Because the entire quantity is to the 1/2 power, or the square root of, when I pull out an r squared and then use the square root, the r squared simplified down to an r, because the square root of r squared is r, and then the rest stays under the radical. The Pythagorean trig identity states that sine squared plus cosine squared equals 1. So 1 plus 1 is then 2, and like terms are then added together to get 2 plus 2 cosine of t. Then there's another trig identity that states that the square root of 2 plus 2 cosine of t is equal to 2 sine of t over 2. And then as you integrate, you get 8r for your final answer.
Is it on? Oh, shit.